This is the second lecture segment on the AltLs utility, picking up from where the first left off. And in the first one, we had reached the point where we were looking at a table of small mode care structs that described how we were going to set the individual letters in these mode strings here that reflect read-write execute permissions in the ls listing. And we looked at the R and the W and the X and even a D flag for directory, but we ran across an interesting twist here in these two entries there, where apparently an S is to be set for the S_ISUID and S_ISGID flags. What are those about? Well, to illustrate, let me do something here. First, there's an ls listing right now with altls.exe, and as you can see, it's readable, writable, executable by me, and I have it readable and executable by the rest of the world. Now, if someone else executed that file, they'd run the program with their permissions, right? Anytime you run a program, it runs under your permissions and rights. You run a VI program and you can open files that you own, but you can't open files that someone else owns, for example. There are, however, a few cases where it is convenient to arrange for an executable file to adopt the permissions or to gain the permissions of the creator of the file. A good example of this is a course that you're probably taking if you're listening to these lectures from me, where we use an executable called turnin. And this is a program you run on Unix, and it submits files to a directory of my designation and evidently has the right to write into directories that I own. And the reason it has that right is that I have set it to run under my permissions when you run it, and thus it can copy into my directories. That's a slightly dangerous thing to do, of course. If I make the file a little, if I make it vulnerable to security attacks of one sort or another, then you can take this program that is running with my permissions and perhaps coax it to do things it oughtn't to do. So when you create a program like that, you are quite careful about how you write it, because it is, after all, going to run on your behalf, no matter who's running it. To make this happen, you set mode bits. It's another part of the file metadata. And an executable file may have the set user ID bit turned on, which means that when it runs, it'll run with the permissions of the owner or creator of the file, not the person running the file. And likewise, a set group ID bit, which has the same effect on the group. Now, just to drive the point home, I'm going to actually change those bits. It turns out that they are changeable with this command, chmod 6, and then 755, and altls.exe. Notice the listing I have right now, which has execute, permission for group and for owner, see Staley, and group none. And now when I ls it, things have changed. There are S's here. Those stand for set user ID or set group ID, and they overlap the original execute bits. In other words, they're saying this file is still executable, but when you do execute it, it's going to have that set user or group ID characteristic. And you can tell from what I just did where in the stmode bits the set user ID bit and the set group ID bit would be. Again, looking at what I have here and then moving over to here, I think we can get them both on screen at the same time. The is UID, S_is UID bit flag. What is that in octal? And what is SGID in octal? Counted as an in-lecture question. You have to make a bit of a guess as to which is which, but you can tell what the two of them are by what I did with the change mod. And the answer is, well, evidently, when I did the change mod, I dropped this 6 up here. And the 6 is apparently a 110. And those are the bits for set group ID and user ID, in that order, in fact. So set user ID is going to be octal 04000, 3 O's after it. So it's way up in the bit, in the mode bits. And then for group, apparently 02000. All right, with the little table now explained, we can go back down to write stats and see how we use it. Once I've done all that work to set that stuff up, all I have to do then is set up a mode string, and modestr_len is 10, and add 1 for the null at the end, and I have my modestr here. And I'm going to start by making everything in it a dash. meaning all the flags are in effect turned off, and put the null at the end, of course. And then I'm going to go through my mode curs array. And I'm going to use a pointer to a mode character and start it at the beginning of the array. And I'm going to test for as long as its flag is true. That's one thing I forgot to mention. The way I did the mode curs array is that I put a guaranteed marker at the end with all 0 values. And when we hit that, we'll stop. It makes it more convenient than having to keep track of the length. So as long as mode char flag is non-zero, we keep going. And in each case, we AND our stmode with that flag. And if the result is true, then we set the appropriate element of the mode string to the appropriate letter, R, W, X, D, or S, as the case may be. And when we're done, our mode string is ready to go. In fact, down here in the final printf that is actually putting the line out, you can see that the first string we will print is our mode string. Okay, well, that's 1 out of 6. Now all we got to do is get information about the current user, or excuse me, owner, I should say, of the file. Well, that is one of the pieces of information in the metadata. STUID is the identifier of the owner of a file, the creator, CStaley in this case. Now, that's an interesting thing, though, because STUID, if you look it up, is an int. And here again, a larger Unix concept being illustrated in this program. Every user in a Unix system has a unique integer identifier. And the number you get depends on when you were added to the system, really. The super user is identifier 0, but we don't know what number we may have. I could have left it as a number, and I would get something largely useless, but what I want to do is convert it to the equivalent name. And there is, conveniently, a system call, actually a library call, I should say, that will do this. Get password UID, and this returns, being passed the integer ID that is kind of the internal representation of a user. It returns a struct with a lot of information about the user whose ID is that number. Among the things in there are the user's name. And we are therefore, I should say it returns a pointer to a struct. We are therefore arrowing the pointer to the struct that is returned and getting the name of the user, and that would be CStaley, for instance. Now, do a bit of Googling, please, on get PWUID and answer a couple in-lecture questions on that. First, where does it get that information? How does it know? There's a particular file in question. And then second, what other field or fields might there be in the struct returned that would give you more information about the user, perhaps? And coming back from a pause, I went and did the research myself just to see what was out there. And there are a lot of good pages on that particular function. And what you'll discover is that it searches what is loosely referred to as the password database, but that really broadly means the user information database. Now, once upon a time, there was only one file that had this information, and it was /etc/password. And that still exists on Unix systems. Even on faked-up Cygwin Unix systems, like the one I'm using for this illustration, ls etc password, and what you'll see here is a bunch of entries that have kind of broken over multiple lines, sorry about that, a username, and then something that is unused, we'll get to that in a minute, a user ID number, apparently I am user 1000 in this little system, a group number, a home directory, oh actually that's right here, all separated by colons, as you can see. Now, in more modern Unix systems, by the way, there are other services that provide this information, stuff like LDAP for network-based file maintenance, or login and password maintenance. So it isn't always in such a simple text file as this, but it's still useful to know that there is an etc password file, and that it is the repository of user information, and it has bigger cousins now that are web services. But the bottom idea remains there is some way for functions like get PWUID to look this stuff up. Is it a system call? Think about that. In-lecture question. Is that a system call? And you know, the answer you might have come up with is, no, it's not, really. All it needs to do is consult a file. It doesn't have to be a system call. It doesn't have to do some fundamental operation involving raw access to the disk or manipulation of memory layout and that sort of thing. So it's a very powerful little command or library function, but it's really not a system call. Yeah. I promised that I'd go back over one thing here. Oh, sorry. Second answer to the lecture question first. I said to find out what other things you could get besides PW name. And as you'll discover, the answer, here, I'll even drop one in here. I don't know if that's readable or not. Is now. This is the struct that you get with the call, and it has, as you can see, the user name, but also, my God, the user password. Well, not really, as we'll see. The user ID, home directory, shell program. There's a lot of information you can get about a user through that little library call. Is password really one of them? Now, if you go back and look at the password file, the one that says unused here, the second in each of these kind of horked up lines, you'll find in most cases they're stars, which means we're not going to tell you. And the password file has asterisks in there. And in the case that I had, it's unused because I'm not using my password at all. This is just a local SIGWIN layout that I use for Unix lectures, so it's not even password protected, my account. You know, a little war story for you. Once upon a time, that field in the etc. password file actually did give the password, and in readable form, except what it would do is take whatever password you had entered. So, you know, my password is change me please. And if I enter that change me please password, it would encrypt it using itself as the key. You had some encryption system that needed a key, and you would use both the password as the thing to be encrypted and also the key to do the encryption. And then you'd throw the password away. And the password file would contain only the encrypted version here in that second field, but publicly readable. Anyone could check it. And what that would mean is that if someone entered a password, you could see if it was the right one by repeating that encryption process and seeing if the encrypted garbage you got was the same as is listed in the etc. password file. Now, at a glance, it sounds like good security. You're not even keeping the original password. You couldn't even get your original password back. You still can't on a Unix system because it's thrown away, and the only thing that's kept is an encrypted version of it. But it turned out to be a huge hole once we got about past the 1970s or so, because, of course, inevitably clever people will take entire dictionaries of words, phrases, other reasonable random things like dog names and birth dates, and encrypt them all in very rapid form, and then see if the encrypted result can be found anywhere in the password file. So everybody whose password was like Lady Gaga or some trivial piece of current culture would get cracked this way because it would just be one of the many phrases that were automatically checked. These days, you don't even get to look at the encrypted version of the password unless you have special privilege. Okay, so back from digression here. We now understand how to get a username and the larger issue of users are identified by number, and there is this database, either textual or more complicated than that gets us information. We can access at least some information about every user. Same goes for groups, and very similar deal here. Get group ID and the group name. That takes care of our first three fields then, permission, modes, username, and group ID. The next one, if you may recall, is the size of the file. And here I used st size from stats, cast it to an unsigned long, and printed it that way. It is not a signed value. It's unsigned, of course. It can't have negative file size. And then the modification date of the file. Now that's more complicated, and again gives us a Unix digression. By the way, the final one, the name of the file, is the easy one that we already have. But that time string, how are we going to get that? Well, the STM time of the file stats gives us the modification time, last mod time of the file. So that's the original data from which we get stuff like March 12th, 1513. But it doesn't provide it in a very usable form. In fact, that's a big integer. I think that's actually several fields in a struct. A single integer, even 4 bytes, is not enough to hold it. It's a count of the number of seconds since the Unix epoch, as it is commonly called, which is the beginning of the year 1970. So talking in, say, the early 20-teens, it's 40 years and change ago, so the time value will be something in the 1 to 2 billion range. A lot of seconds have gone by since 1970. Now, the value is, of course, singularly useless as such, so we need to convert it into something humanly readable. And this opens a whole interesting discussion, and we'll do a very brief talk about it, regarding the representation of time in general. First of all, almost all systems, Windows, Unix, what have you, do use some marker of the start of time and some count of units from that time. In the Unix case, 1970 and seconds. Now, the need, of course, exists to convert that to something usable, but it's really even deeper than that, because it's not the same time everywhere on the planet, of course. Time zones make a difference. Indeed, it's not even the same date everywhere on the planet. You are not technically the same age everywhere on the planet, especially if it's your birthday. Some places you're still a year younger, and some you're a year older. So you have to deal with all those complexities. And not only that, of course, but time zones include such issues as daylight savings time. Oh my God. Which, of course, differs very much politically. There are states in the U.S. that have 4 different times at the same time in the same state, because they're 2 different time zones and 2 different daylight savings time rules. And it's a very human mess. Some way of converting that is needed. Now, the standard, of course, if you don't want to deal with all that, is to use Greenwich Mean Time, or Universal Time, as it's more modernly referred to. And the old function, GM time, using the older notation Greenwich Mean, does exactly that. It takes the seconds since the epoch and returns to you a structure that has fields that tell you what hour and minute and month and day and year and so forth it is. So you get the time broken out with individual numbers for the year and the month and the day. That's better, but it's still Greenwich Mean Time, and it's still a bunch of integers rather than some neatly formatted string. So there exists also a function ASCII time, that converts Greenwich Mean Time figures and takes into account the current time zone and daylight savings time and so forth, and returns then a string that you could print. And that is the one we actually want, with one small problem. For some inexplicable reason, the string has a return smacked on the end of it. So that's usually not too useful to have, and we are here doing a index of the very final non-null character of the string, setting that to null to in effect drop, as the comment indicates, the stupid return. And finally, we have a time string we can print. Now, what are the bigger issues here, just to be aware of? The mechanism, as I mentioned already, by which time is usually marked. The need then to convert that not only to human readable form, but also with respect to all the political issues surrounding time zones and daylight savings time. And then also, of course, varying time formats that go across different cultures. ASCII has a default that it uses, which is generally acceptable in U.S. culture, but you can give it format strings as an alternative, and it will format the time in different ways. And just to drive home the value of having different formats for different cultures, I'll write a little comment in here, since it's the easy way to put a note up. This is what date? 4/1/13, or if you like, 4-1-13, and what have you. Well, most United States citizens will read that as April 1st, year 2013. Unfortunately, most of the rest of the world rather sensibly reads it as the 4th of January, April 2013, assuming that one would normally, of course, do date, then month, then year in ascending order of size, instead of swapping the two in that funny way. So when you are dealing with time representations, then the full list is: know how the time is represented internally, usually as a raw count; know how the time is convertible into the appropriate figure for just number of hours, days, and so forth, including time zone issues and daylight savings time; and then finally know how to convert that to a format that is culturally recognizable in whatever context you're programming. Okay, so coming on down here finally to the list program that we digressed from earlier. The rest of this we will look at in a third lecture segment because we're running out of time here. And so we will finish that up in section 3.